Draw the Lewis structure for O3 on O3, which is also known as ozone. And these are the one that oxygen and oxygen, oxygen. These three oxygens are bonded together. And in order for them to form a molecule, at least, there should be a single bond together. And this is something that we need to further develop to understand the Lewis structures. And where's an oxygen? Right here. There are the 6. So each oxygen has 6 valence electrons. And so when I draw this, I can draw, okay, if I have 1, 2, 3, 4, 5, 6, and then there is the 2 electron coming from the central oxygen, so I can do that. And then this one too, if I do 1, 2, 3, 4, 5, 6, and I have 2 electrons coming from the central. So by doing it, these 2 bonds containing 4 valence electron would come out from the central oxygen, and so therefore you need 2 more electrons, and that's the right there. So by drawing this, you essentially, because the electrons on those oxygen on the outside will have we have more than what they have, and so they develop the former charges of -1, -1, and there is a +2. This is a very highly unlikely scenario. So what they will do is, okay, so I have too many electrons, for example, on this side. They're going to essentially share the electron by forming the double bond. So by doing so, oxygen will form the double bond with another oxygen, and then this will be a very good scenario. And then in that case, well, there was this one, and the other one will just stay the same as it is. Okay, so minus and the plus. So this will be one of the hybridization structures. And if you think about why not? How about the other one doing the same thing? And then you're thinking about, can I do this way? And I can have another extra the lone pairs to form another double bond. In that case, this one is really cannot happening, okay, because this is a second row atom, oxygen, so they cannot have more than 8 electrons. Unlike sulfur, this one must obey the octet rule, and this one cannot happening this way. So this is the one in the top, and also the resonance structure of double bond here, single bond there, with 3 lone pairs with a negative former charges, and I guess this is a lone pairs with a positive former charges. They are forming these resonance structures, and this is the right one. And the question is hybridization of central oxygen. So if you're looking at the count number of sigma bonding or the lone pairs, you have 1 here, you have 1 here, and let's say you have 1. You have a 3 I guess coordination, so that makes it Sp2 hybridization. So the answer for this one is B. The problem continues for understanding the Lewis structure of a molecule. Here is a case for what we call the H3O+, and this is called hydronium ion. And this is essentially made from, when you have a water, H2O, and meet with H+, H+ is finding the place to attach to the water, and they became H2H3O+. And just want to know where those things are more located. And if you think about water, and they have 2 lone pairs here, and then there is a hydrogen bonding here, and then this one now H+, which is just proton, and this lone pair electrons are attracted by the H plus, and so essentially they form this bond. So now you have H, H, H with the lone pairs there. Okay, and so by doing it, actually, if you're looking at the former charges scenario, the former charges of a central oxygen is essentially what? +1. Okay, so that's why the reason is because this one has 6 valence electron, but they have 2 lone pairs, 2 electrons from lone pairs, and you have a 6 bonded electron, only half of them being count. And so overall, this this central oxygen feel like have 5 electrons, but your valence electron is 6. Therefore, therefore, if you compare these two together, they are in short of 1. So the 6 minus 5 is 1 plus 1. So this is why that you have developed the former charges of 1, and they essentially show overall charges is shown up here. Regardless, the hybridization still continues to be the same. The waters in the molecule, the oxygen still have 1, 2, 3, 4. They are the tetrahedral, and sp tetrahedral means 4, sp3. So that's here too. 1, 2, 3 bonds and 1 lone pairs. So they are still have a tetrahedral electron group geometry, and that means sp3 hybridization. So this is actually a quite easy problem, sp3 hybridization. Okay, this problem is understanding the molecule. Particularly, this is an organic molecule, and this is how people write. And there are sigma bonds and there are pi bonds. When you see the double bond, one must be sigma, the other must be pi bonding. And if you're looking at the structure, let's look at this the structure of this molecule. You have 1, 2, 3, 4 carbons, and then this is what we call the acid. So it is actually a butanoic acid, okay? Because there are 4 carbons, it's butane. So butane-based acid is a butanoic acid. So I'm going to draw the 4 carbons. They all need to bond it together. And then this is H bonded to first carbon. And the second one seems like there's only 1 hydrogen. So I should do that. The third one seems like there's 1 hydrogen. And you need to now know CO2H, which is a CO2H, is a C double bond with O and H. This is what we call the carboxylic acid group, and this people call CO2H. Sometimes people write COOH, and that means the same thing as carboxylic acid up there. And so now, am I done? And actually not really. If you're paying attention to this one, this carbon has 3 bonds, and it should be complete as it is. So the way that I can make this structure real, I should form double bonds here. So that's really the key point of this writing the structure here. So how many pi bonds do I have? I have pi bond. Let me try to use a blue color here. So I have a 1 pi bond here, right here, and there's another pi bond here. So there's a 1 pi bond. There's another pi bond within the 2 double bonds. So I have 2 pi bonds, and how many? Okay, there are 2 pi bonds. Actually, this is not enough for me to figure out. So let me write down count the number of sigma bond. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 11. So I have 11 sigma and 2 pi bonding. So the answer is D here.